Hello friends, today I will discuss the DC motors. Here the topics are what is the necessity of DC motors, then what is the construction of the DC motors, next Fleming's left hand rule, definition of motor, principle of motor, back EMF, voltage and power equations for the DC motors and the types of motors, then series motor, shunt motor and their related equations like voltage equation and power equation for this series motor and shunt motor. So first of all, why should we study these DC motors? That is, what is the necessity of this? In reality, we need certain equipment, we are using them. Some motors are for high starting torque purpose, some motors are for constant speed purpose. Suppose we take elevators or steel mills, rolling mills, locomotives, excavators. All these devices use high starting torque. For this, we need what is called DC series motors. Whereas there are applications where we need the constant speed, that is conveyors, spinning machines, blowers, fans, lathe machines, lift pumps, that is centrifugal pumps. So we need constant speed machines. For this we use DC shunt motors. So keeping this in view, it is necessary to know their construction, their principle, etc. Let me consider first what is the necessity of Fleming's left hand rule. This Fleming's left hand rule is used for knowing the direction of rotation of the motor. As per this law, the first finger shows the direction of the magnetic flux, that is this, whereas the second finger indicates the direction of the current flowing in the conductors. When these are properly placed in the motor, then the motor will experience the mechanical force that is called motion of the or direction of the rotation of the motor, which is indicated by the thumb like this. Here thumb, first finger and the second finger all are perpendicular to each other like this. Coming to the general expression or general definition of the motor is that it takes the electrical input but gives the mechanical output like this. What are the electrical parameters? That is nothing but applied voltage, and automatically the motor takes the current. These two are the input parameters, whereas the output is the rotation, that is angular velocity, and the torque. Now let us see the principle of operation of DC motor. So for the DC motor, we need three parameters. One is called the magnetic field, the other is current direction in the motor conductors, that is nothing but armature. So that we get the ultimately the mechanical force experienced by the conductors. To show it simple, look at this. This is the magnets. This is south pole, this is north pole. And exactly perpendicular to that, there is a conductor like this which carries current in this direction, that is in the direction of uh, second finger, that is out of the paper, whereas the field lines will flow from left to right on the paper. Then the conductor will experience the force in the direction of thumb, that is on the paper in the y direction, like this. This means whenever there is a current carrying conductor placed in a magnetic field, it experiences a mechanical force like this. Coming to the construction of the DC motor, this is the diagram. Here, the outer part is called the yoke, which is also called a frame. This supports the stator, that is, so inside there is a laminated core. So here this is the field core and this is the armature, and in these slots armature conductors are placed in specific way, that may be lap winding or wave winding. And this is the shaft. On this shaft, this armature core is placed and armature core carries the armature conductors, and on the same shaft there is another segment that is called commutator. So this commutator is electrically connected to the armature conductors, and this commutator will carry on the commutator brushes are also placed, and this is the field code, this is one field code, this is another field code, this is another field code. That means this motor is a 4-pole DC motor. To avoid the armature effects, armature reaction effect, so there are interpoles also between the main poles. These four are main poles. Similarly, in between there are interpoles. And this field course carries what is called field winding. Once those field windings are connected to the supply, then they carry the current and the current produces magnetic poles here. And this armature will be connected to the static supply via brushes and commutator so that it receives power while moving. So once there is a current flowing in the armature conductors, when there is a magnetic field produced by these main poles and the interpoles, so then the armature bound to experience mechanical force. So if you further look at the construction, so if you remove the armature, then we find the motor like this. These are called legs or feet, and this is called the frame. This is also called yoke, which gives the mechanical protection for the motor, and this is called the eye or the lift eye. This is used for lifting the motor, and this is the terminal box where supply is given, DC supply is given to the pole field winding and armature winding. If we further open it properly, we find armature means it is like this. This is the shaft, and over the shaft there is a commutator, and just besides that there is a armature core, and in the armature core there are slots. In these slots armature winding is placed, that we can see here, windings. This is the other end of the shaft. Similarly, if you look at the stator, this is the stator, so which we have already seen. So this stator consists of the field course, and field course carries the field winding, and that winding we can show like this. This is called the field core, or this is also pole, and this part is called the pole shoe, and this is called the pole. Broadly speaking, motor construction means there are only two parts. One is called the stator, the other is called the rotor. So here a rotor carries the armature core, armature carries the armature conductors, and the rotor shaft carries the armature core, and it also carries what is called the commutator, and the commutator carries the movable brushes. Commutator looks like this. These are the brushes. So these are normally carbon made brushes, and these brushes will be connected to the DC supply like this with a red wire and the blue wire. And this is the commutator. So here there are close to it looks like a armature, and over this commutator segments, while commutator rotates, that is when armature rotates, automatically commutator also rotates due to the rotation of the shaft, but the brushes remain on the or in contact with the commutator segments, and brushes are always connected with the DC supply so that it supplies the current to the armature winding via commutator segments. Coming to the classification of DC motors, here we find the three types. One is called separately excited motors, the other one is called self-excited motor, the third one is called the permanent magnet DC motors. These permanent magnet motors are normally used in small applications like toys. Similarly, separately excited motors are used normally in the laboratories for experimental purpose, whereas self-excited motors are normally used in real applications. Under self-excited motors, again there is a classification called shunt field winding, shunt motor, series motor, and compound motor. Again, in the compound motors, again there is a classification called cumulative compound motor, differential compound motors. Under this category, again we find long shunt compound motor, the other is short shunt compound motor. Means this long shunt compound motor can also act as a cumulative compound motor or differential compound motor. Similarly, short shunt compound motor will also can act as cumulative compound motor or differential compound motor. But in this topic, I restrict the explanation for shunt field motors and series field motors. So suppose we draw the diagrams for these motors, they appear like this. Classification of DC motors under this self-excited motors. Self-excited motors means the field current comes through a separate source, that is separate battery like this, and the battery is connected in series with a high resistance like this, variable resistance, and the motor is connected to another DC supply. Means motor armature is supplied by a separate source and the field winding is supplied by another source. So that is the reason it is called self-excited motor. Coming to the self-excited motors, here the field winding and the motor armature are connected together in certain fashion. Suppose the field winding is connected in series with the armature of the motor, then that motor is called series motor or series field excited motor. Suppose the field winding is connected across the armature of the motor and connected to the DC supply, then it is called the shunt motor like this. Look at this. This is the armature and the field winding is connected across the armature. So it is called the shunt motor. Whereas here, this is the armature of the motor. This is the field winding. They are connected in series. So it is called the series motor. Similarly, compound motors, long shunt compound motor and short shunt compound motor. So it's observed that here series field winding is connected in series with the armature and this combination is connected across the supply, and across the supply the shunt field winding is connected. So this is called shunt field winding, this is called series field winding, and this type of connection is called the long shunt compound motor. Similarly, if the shunt field winding is connected directly across the motor armature and the series field winding is connected in series with the supply, then it is called the short shunt compound motor. Let us discuss about back EMF, voltage equation and power equations in the DC motor. In general, let us assume that there is a magnetic field surrounded here across the armature of the motor like this. This is the motor armature and the motor armature is connected to the DC supply like this. Once motor is connected to the DC supply, it draws the current, but the armature resistance of the motor is very less. It's approximately less than 1 ohm. So it's something like 0.5 ohms or zero point 0.1 ohms. Whereas the applied voltage is normally 220 volts. So when this condition exists, it draws very high current. So due to the Lenz's law, when the supply is given to the DC motor, the motor accelerates its speed and also produces a EMF in the motor armature called the back EMF. This back EMF has the polarity opposite to the supply polarity and it is almost near to the applied voltage. If this circuit is drawn like this, armature resistance is placed like this RA, and the back EMF or the voltage induced in the motor armature whose polarity is opposite to the applied voltage, then it will be represented like this. So since the back EMF is almost near to the applied voltage, so the current that flows in the armature of the motor is much restricted, that is V minus EB divided by RA under running conditions. In practice, at the beginning, for all motors there is a starter. Starter means very high starting resistance. So with this, when the voltage is applied to the DC motors, it has the two functions. One is responsible for producing the back EMF in the motor. The other is it is also responsible for the voltage drop in the armature resistance. So if we relate this applied voltage with the back EMF and the armature voltage drop, that is IA/RA, then that equation is called the voltage equation of the DC motor. That is V is equal to EB plus IA/RA. So this EB is called the back EMF and IA/RA is called the armature current into armature resistance. So this equation V is equal to EB plus IA/RA is called the voltage equation of the DC motor. Suppose this equation is multiplied on both the sides with the armature current, then the equation will become like this: V into Ia is equal to EB into Ia plus Ia square into RA. Here V into Ia becomes input power to the motor, whereas EBIA is called the power developed by the armature, whereas Ia square RA is called the armature copper loss. So this equation, that is V into Ia is equal to EBIA plus Ia square RA, is called the power equation of the DC motor. Suppose we want to know what is the condition for maximum power developed in the DC motors. For this condition, so what we do is we write the mechanical power developed by the motor, which is equal to EB into Ia, and we know the power equation. From that we can write EBIA is equal to VIA minus Ia square RA. That is, from this equation we can write EBIA is equal to V into Ia minus Ia square RA. Once this is written, differentiate on both the sides with respect to armature current. From that we get what is the condition for maximum power, that is dPm divided by dIa is equal to V minus 2Ia RA. So at maximum mechanical power developed, this differentiation or slope becomes equal to 0. So from this we get V minus 2 RA Ia is equal to 0. From this it can be observed that applied voltage is equal to 2 into Ia RA. And from this we can also write Ia RA is equal to V by 2. That is, when the voltage drop across the armature is half the applied voltage, then the motor will develop maximum mechanical power. Suppose here we take the DC series motor. We already saw how the DC motor is connected. This is a self-excited motor example, and this is the armature of the series motor, and this armature is connected in series with the field winding. And this field winding resistance is very low. It's something like 100. This DC series motor series field winding resistance is, it's approximately 0.05 ohms. It's just almost similar to the armature resistance. And this is the applied voltage V. And in this motor, the field current and the armature current are one and the same because they are in series. So we write series field current is equal to the load current, that is also equal to the armature current. So when the DC supply is applied to the DC series motor, it also produces what is called the back EMF. So from this, the current equation can be written as IL is equal to, that is load current is equal to series field current, and that is equal to the armature current. So from this, voltage equation can be written as V is equal to EB plus ISC RSE plus IA RSE. Multiplying on both the sides, then we get the equation V into IA is equal to EB IA, IA square RA, IA square RSE. So from this, it can be observed that EBIA is nothing but mechanical power developed in the armature. This is nothing but output of the motor. And whereas IA square RA is nothing but armature copper loss. And whereas IA square RSC is nothing but copper loss in the series field winding of the series motor. So in the DC series motor, we have seen the current relations, the voltage equation, that is current is IL is equal to ISC is equal to IA, and whereas the voltage equation, that is supply voltage is equal to EB plus IA RSA plus IA RSA. So we also observe that the mechanical power developed in this DC series motor is EB into IA, and there are losses, copper losses in the motor. Put together, mechanical power developed and the armature copper losses and the field copper losses is called the input power, that is V into IA. So let us move to the another motor called a DC shunt motor. In this case, the supply is connected across the armature and also across the shunt field winding. Here also the shunt field winding resistance is more than 100 ohms. So sometimes it will be 250 ohms. Whereas the armature resistance is something like less than 1 ohm, that is 0.01 ohm, or maximum worst case it will be 1 ohm. So because the series field winding resistance is very high, so it draws very less current, that is approximately 10% of the main current. And whereas this armature current it draws maximum current from the supply, and this current we represent with IA, whereas the shunt field current we represent with ISH. Whereas the input current is called the load current, this is also called IL. Once the DC supply is given to the DC shunt motor, the armature of the motor produces a back EMF which opposes the applied voltage so that it draws less current from the DC supply. And from this circuit, it can be written using the KCL, that is the input current is equal to armature current plus field current, that is shunt field current ISH, IA plus ISH. Then writing the voltage equation for this loop, we can write V is equal to EB plus IA RA. So here IA RA means it is the armature copper loss or armature voltage drop, whereas EB is the back EMF. So the equation relating applied voltage, back EMF, voltage drop across the armature resistance is called the voltage equation of the DC motor. Multiplying on both the sides with IA, the equation becomes V into IA is equal to EB into IA plus IA square RA. And here EB is called the back EMF and IA RA is IA square RA is nothing but armature copper loss, and EBIA is called the mechanical power developed by the DC shunt motor, and V into IA is called the electrical input to the motor. As we have seen, motor means It takes the electrical power and gives the mechanical output. So V into Ia is nothing but electrical input power, whereas EB into Ia is the mechanical power output. And this Ia square RA is nothing but the copper loss. Let me summarize once the video. So here we observed what is the necessity of studying the DC motors. So why should we study the DC series motor for high starting torque? And why should we study uh, shunt motors, that is for constant speed purpose? And we have seen the construction of the DC motor, and which consists of basically two parts. One is called stator, the other is called a rotor. And the stator consists of several parts and the rotor also consists of several parts. So that also we have discussed. Next, we have seen what is the purpose of Fleming's left hand rule. So this Fleming's left hand rule says if the magnetic field and the current is provided in the conductor, it provides the direction of motion of the motor, and it is also observed in the definition of motor, that is nothing but when there is a magnetic field production and there is a conductor carrying conductor, then the motor experience mechanical force, that is it produces mechanical output by taking the electrical input. And coming to the principle of motor, when there is a current carrying conductor placed in proper way in the magnetic field, it produces a mechanical force or experience the mechanical force. Similarly, back EMF. When the voltage is applied to any DC motor, to protect the armature, it produces back EMF which is almost near to the applied voltage. And we have seen what is voltage equation and what is power equation, and we also observed what is the condition for getting the maximum power from the DC motors. That is, when voltage drop across the armature resistance is equal to the half the applied voltage. Then we have seen the what are the types of DC motors. So they are nothing but self-excited motors. The other is called the separately excited motors and permanent magnet motors. And we have seen the self-excited motors, series motor and shunt motor. And we have seen their voltage equations and power equations. Similarly, in the shunt motor also. And we have seen the resistance of the armature is less than 1 ohm. Similarly, in case of DC series motor, the series field winding resistance is also very less, that is 0.05 ohms. And whereas the shunt field winding resistance is varies from 100 ohms to 250 ohms.